There is nothing but principal component analysis. This is when we formulate the problem, we never consider this is a principal component analysis, is like a statistical approach, random process or something. But we do differently. We only use everything, nothing random. It's just a fine set feeding. It's the knowledge, chapter 2, chapter 3, and chapter 4. Then this is a paper, and applying hyperspectral imaging lots. Now it becomes a high citation paper. But it is published in IEEE translation, signal processing. Most of the hyperspectral imaging paper published in IEEE translation, geoscience and remote sensing. That's also a very, very good journal. Now you sense, the more and more the powerfulness of convex optimization. This is just one example. Okay, the next, let me finish this. We still have some time, a little time. Suppose this. Sorry, let's look at this problem. We want to solve this. This is a low-rank approximation. This is a data matrix. Please find a matrix Z. It's data matrix M times L. M, as I mentioned, it could be a very huge number. L is a huge number, but your data is a low-rank space. So that's a finite Z, approximation to capital X. But the rank is only capital N. What's the solution? The solution is nothing but Z using the data X. It's a single value decomposition to keep the capital N component. That's the solution. This is the solution. This is a UIVI, R and sigma I, are eigenvalue, left eigenvector, single vector, right single vector of X. This is well known. But the way we solve is using convex optimization rather than linear algebra. The problem is, again, this is the problem you want to solve. I'm asking you, is it convex problem? You will check. Objective function, is that objective function convex function? This is a variable at Z. Two known square, not two known, from any known square is convex function. Unknown variable, this is X is a constant, it's a beta matrix. It's a affine function of Z. The composition is convex, right? So objective function fine, convex function. This is a constraint set is a convex, right? No constraint for Z. M times L. But these constraints, is that convex constraint? It's inequality constraints. Rank Z is not convex function, right? Do you remember? Rank is not convex function, right? Okay, so how do we handle this? This is rank. Like the previous problem, this is previous problem. this one, we put it. This is not easy to handle. So a fine dimension is n minus 1. How do you handle this? Or for the problem here. How do we handle this? Right, this is the hard part. The way we can do this, we represent z, the variable, or changing variable. Represent it in terms of c and y. So c times y. C is a unitary matrix, semi-unitary matrix. C is m times n, y is n times l. So with this reformulation, we can show that. See? Look at this is z. Z is c times y. And by the Sylvester rank inequality. It's rank C plus rank Y minus n here. But rank C, the rank is n. This is this right? This is rank C. N. This is chapter 1, linear algebra. So we end up with rank y less than equal to rank z. Then rank z is less than n1 because z is c times y. Then by the rank inequality, so rank is the minimum of rank c and rank y. But y is a huge matrix. Minimum. The minimum, even y, in rank, the maximum is n, right? In C, rank is n. This is also less than equal to n. So it is n, because the n, n times n matrix, its rank is less than both. And then goes to the minimum. Yeah? Okay, so we end up this is n, less than equal to n. So we end up, so we put over here. So with this reformulation, we end up with z disappear, and y rank y automatically has rank less than capital N. So in other words, this constraint, rank constraint, disappear. We just have this problem. But this is a new variable, C, transpose C, and semi-unitary, and this is the problem we can solve. But also inner layer, this is inner layer, outer layer. You have two variables, capital C and capital Y. Inner layer is unconstrained, right? So in minimization, you can mean, fine. So we have just presented why you can use it. So this is the inner minimization. It's a quadratic function or complex function of y. Right? So you can take gradient equals 0 to get optimal line, it's c times x. Then you put it back and to the objective function, you get this. You put it back, then you end up solve the outer minimization. auto-minimization happen to have the same form as you have seen in the previous example, corresponding to x replaced by u. So that's wonderful. So you can apply, you end up with the solution. I skipped those tedious and mathematical manipulation. So this is the result. You can see when you have an engineering problem, originally you don't know how to handle it. You need to, when you have a very solid foundation, linear algebra, calculus, as well as Convex optimization put together. And you can reformulate. You can replace something with some way, alternative way, that you may solve it. Of course, when I tell you the solution, then you can learn. But if I didn't tell you, like homework, sometimes our examination problem is very hard. Then you need lots of time to solve it. You're even not able to solve it. When I show you the solution, you may easily to understand why. But if you have seen the solution, then that means your level is not, you didn't reach that level. When you see the solution, then you lose the opportunity to upgrade your level. So try to solve it yourself using your foundation. Try to do that. So anytime, if you can, you need to, in other words, you're not like high school students. You have your problem is selection. So 选择题，这样用猜的题目。But now you don't have those kind of selections. Even your selection, you need to tell me why. Logical reasoning. Logical reasoning is your capability for innovative research. So that requires a solid foundation. Otherwise, you can read the paper, publish the paper more. The authors are so smart, after you read, you can learn, but your level is not like that high yet. So different. So the only way you can to establish your innovation or capability research is establish a very, very solid foundation on linear algebra, Convex optimization. You are able to analyze, you are able to reformulate your problem, then you will be outstanding researcher in the future. Finally, this is so far we haven't seen a constraint optimization. This is a constraint optimization. You are not able to use. Gradient equal to 0. This is a problem. For example, this is the problem you want to solve. Unknown variables nu and lambda. Is this problem convex? Exponential function. Exponential function is a convex function, right? Then it's your variable is here. It's a fine function. Lambda I minus 2 minus 1. Lambda I variable, nu variable. So there's an exponential function composition with a fine function. So it's convex. So the second term is convex. This is a linear function. Linear is a convex function. So the sum of convex function is convex function. Weighted sum, right? So this is a convex problem. Can you solve it using optimality criterion 4.26? This is the optimization criteria. Sometimes yes, sometimes you can guess your optimal solution. This new has no constraint. Just a real number, no constraint. But lambda, yes. Lambda 1, lambda 2, they must be non-negative. They are not unconstrained. So they are constrained here. So can you use 4.26? The rational derivative must be greater than equal to 0. But you can try. You can try. But there are two parts of the variables. We can use the remark, like minimum. Usually in the minimization, we try to use to handle that one is easier to handle. Yeah. 好解的先摆平啊 ，easy one to solve first. The inner minimization is unconstrained. Objective function is convex, greater equal to 0. Immediately you get the solution in terms of lambda I. Then put new star back. The problem becomes like this. The objective function becomes a log, like this. Like this. Then you solve these problems with lambda greater than equal to 0. This is component-wise inequality. So some constraint here. Right? You will say, no, that's guess. We still assume our solution. Assume our solution is in the interior of the feasible set. 我们假设这样好啊，那你就把它算它的 gradient， 令它等于零去解得出来 ，good， you will get the solution. However, if you do this, you will see there's all the terms in this vector. They are strictly positive. So no solution equal, you put it, set it equal to 0, you end up with no solution. Your solution must be on the boundary, right? So you have to use 4.26. Here you use a gradient equal to 0 as a symbol. And for this is a 26. 26 is this. We don't know optimal. This is the rational derivative must be greater than 0 or none in the feasible set. Because the first this guy is strictly greater than 0, and the lambda star, because you want to find a lambda star, optimal lambda star, such that this is greater than 0. In other words, this vector is in K, interior K, lambda minus lambda star must be in the interior, is a component of K star, dual cone. The vector inner product must be greater than equal to 0. Because time is up, so turns out the optimal solution is 0. You can see this minus this is a non-zero vector in 0, in the dual cone or original cone, strictly greater than 0. So the inner product is greater than equal to 0. That's clear. So the optimal solution you can infer is a 0. So you have lambda star, P star is here you put it 0. Right? Log n. Okay, log n. Then there's the optimal solution. Then you have lambda. Then you put lambda here, 0. You could add log n minus 1. So in other words, the optimality criterion, 4.26, 这个 optimality criterion, not so easy to apply, 不大容易用. This is a dimensions are very low. Here, very low. If it's a matrix or any other kind, or gradient, is very simple example. So this criterion, in general, not easy to apply, except for low dimension case, and the solution happened to be the material that can reduce to gradient equal to 0. Otherwise, not so easy to apply. But it is true, theoretically, it's correct. So that's why we need to use other approach, equivalent alternative approach, PKD conditions, that relies on duality theory to be introduced in chapter 9. Okay, let's stop here today. So next time, next Wednesday, we start from here. Today is November 20. Any questions?